So far, we have used mathematical induction to prove statements usually involving series, but we can also use induction to prove other types of statements, such as divisibility. So we're going to look at a divisibility proof in this video, and before we do, we just need to make sure we're on the same page about a few things. So let's say that we have a number n, and n is divisible by 2. What does this mean? Well, 2 divides perfectly into n, leaving no remainder. Okay, so this seems fine so far. So what could n be? What are some possible values of n? Now remember, the number n is a natural number, so a counting number. It can't be 1, but it could be 2, can't be 3, but it could be 4, 6, 8, 10, and so on, right? So all the even numbers, they are all numbers that are divisible by 2. But notice in generating this list here, we are using multiplication, aren't we? We're saying 2 times 1 gives us 2, and then 2 times 2 gives us 4, 2 times 3 gives us 6, and so on. What do we see? Well, we've got the number 2 starting off, and that kind of makes sense because we're talking about a case where our number n must be divisible by 2, but then we have just a list of all the counting numbers, 1, 2, 3, 4, 5, and so on. So in general, our number n can be expressed as 2 times some other natural number. Right, p just belongs to the set of natural numbers or counting numbers. And this way of expressing a value that is divisible by 2 in this case, or it would work for any other numbers, is quite critical to how we set up our induction proofs. So just to be clear, this was an example for 2, but if we said 3, then it works in exactly the same way. Likewise for 4, 5, and so on. Alright, let's jump into our example. Prove by induction that n outside of n plus 1 is divisible by 2 for any integer n greater than or equal to 1. Alright, step 1. Prove true for n equals 1. So let's start with substituting in 1 in place of n. When we do this, we see that we get 1 times 2, which is 2. Now, since 2 is divisible by 2, we can say that it is therefore true for n equals 1. Right, on to step 2. Assume true for n equals k. But what is it exactly that we are assuming here? Well, we are assuming that k outside of k plus 1 is divisible by 2. But in order to help us in step 3, we actually want to set this expression, k outside of k plus 1, equal to something. And this is where we say, if it's divisible by 2, like we've assumed, then it can be expressed as 2 times some other natural number, like we talked about before the example. So we should state that p is an integer greater than 1 greater than or equal to 1 or a natural number. But this is now something that will help us for step 3. So let's do that now. Prove true for n equals k plus 1. So like we've done in previous induction questions, let's actually write out what we're required to prove. And this time, instead of k times k plus 1, we have k plus 1 multiplied by k plus 1 plus 1. Right, so we've now rewritten this with k plus 1, okay, instead. And once again, we want to show that this expression is divisible by 2. So it can be expressed as 2 times some natural number. Now it's not going to be p this time, it's going to be some other natural number. So we'll call it q. And just tidying this bit up here, this is k plus 1 times k plus 2. And once again, good idea to state that q is a natural number. Alrighty, so how are we going to do this? Well, let's start with the left-hand side expression, the k plus 1 times k plus 2. And we need to somehow involve our step 2, which had a k outside of k plus 1. Now we can see a k plus 1 here, which is good. And there's also a k in the second brackets. And we know that if we did an expansion, we would have the k multiplied by what's in the first brackets, and also the 2 multiplied by what's in the first brackets. So rather than doing a full expansion, let's just show that. So k multiplied by k plus 1, and then we also have 2 multiplied by k plus 1. Now that we can see k outside of k plus 1, we can use step 2. So we're going to replace this with 2p. And we still have 2 outside of k plus 1 tagging on the end here. Now remember, it's always a good idea to state when you have used step 2. Now remember, our aim is to show that this left-hand side is equal to 2 times some value, q, as we've called it. So if we can drag a 2 out the front of this entire expression, which we can, what are we left with? P plus this k plus 1. And remember, p and k are both just different natural numbers, which means this entire expression, p plus k plus 1, is also just some natural number, and in fact, we'll call it q. And so we have shown that the left-hand side is divisible by 2 as it can be expressed in the form 2 times some natural number q. So this is therefore true for n equals k plus 1. Now that we have done all 3 steps of the mathematical induction process, we would finish with conclusion, and we're done. Great work.